So basically this is just a little bit more memorization. The inverse trigonometric functions have their own formulas just like the regular trigonometric functions did. So these are the ones to memorize. The derivative of the inverse sine of x. And remember, inverse sine is just saying if we know what sine is, what angle is going to be associated with that sine. So it's just going the other way from taking the sine, cosine, and tangent. This has a very specific formula, 1 over the square root of 1 minus x squared. But this is only for x is between -1 and 1. Remember that sine -1 of x, inverse sine, is also written as arc sine of x. Okay, so there's one of our formulas. The next one's pretty similar, derivative of the inverse cosine of x. Almost exactly the same, but there's a -1 instead of a +1. Again, x has to be between -1 and +1, and inverse cosine of x is also written arc cosine of x. The final one that we work with is inverse tangent. This is a little bit different. There's no domain restrictions. Or like that. Secant, cosecant, cotangent, those inverses also do have their own formulas, but they don't show up on the AP test. So you can look them up if you want, but I won't ask you to memorize them. Now, these are good to memorize, but if you have a calculator, don't bother with them. Always, 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 if you have a calculator, just pop it in the calculator. You can do it using the second button, then the sine button. So that's right here. Second, and then sine. You want the little sine -1? There you go. Do the same for inverse cosine of x and inverse tangent of x using the cosine and tangent buttons. So we've got inverse cosine right there, inverse tangent right there. Okay, let's do an example. These are pretty simple. You just have to memorize them. Find f prime of x if f of x equals the inverse tangent of x. F prime of x, just memorize it right there. Ta-da! So those ones you've either got them memorized or you don't. Other inverse functions, it's a little more complicated. These are regular inverse functions. Imagine f of x has an inverse function f to the negative 1 of x. You know that the derivative of f of x at the point a comma b equals c. Then the derivative of the inverse function at the point b comma a. Notice this is reversed. So this was a comma b, this is b comma a, is 1 over c. So whatever the derivative is of f of x at a comma b, the derivative of the inverse of x of f of x at b comma a is the reciprocal of that. Let's look at why this is true. Inverse functions are reflections of each other across the line y equals x. This means x and y are switched. So, for example, if we have our axes right here, let's say we've got one function. This is y equals 2x. The inverse function, as we know from working with exponential and logarithmic functions, the inverse function is going to be y equals log base 2 of x. And if we graph that, it's basically just a mirror image right across this diagonal line here. They've just sort of been reflected. And so what that means is that x and y are switched. So this point here is 0, 1. This point here, for example, is 1, 2. And over here it's the other way around. This is 1, 0. This is 2, 1. And that means that when we draw the slopes of the tangent lines here, the slope here and the slope here are going to be flipped as well. This, the rise over run, y over x, change in y over change in x, has been flipped over here to be taking the other variable's place. The change in y here is the change in x here, And the change in x here is the change in y there. That's why it's the reciprocal, because basically the x and the y have changed places, and for the slope, that means that it flips it over. So let's write that down just as a summary. The derivative is the slope of the tangent line, and reflecting the curve across the line y equals x reverses the rise and the run. That makes the slope the reciprocal. Also notice that here 1, 2 corresponds to 2, 1. That's why we have the AB versus the BA. Let's do a couple of examples of those. We are given the function f of x and told that at the point 3, 5, f prime of 3 equals 4. If g of x is the inverse of f of x, what is g prime of 5? So here's the logic that we're using. Because g is the inverse of f, at the point 5, 3, that's the reverse of 3, 5, the derivative of g is the reciprocal of f at 3, 5. Notice this versus that, they're reversed. We're told f prime of 3 equals 4, so g prime of 5 is the reciprocal of that. We can also do ones that involve taking actual derivatives. If f of x equals x squared plus 1, and g of x is the inverse of f of x, and we know that g of 4 equals 2, what is the value of g prime of 4? So here's our logic. We want to find g prime of 4, and we know for 2 is a point on g. X is 4, y is 2. Since f and g are inverses, the point 2, 4, again this is reversed, is a point on f, and g prime of 4 is the reciprocal of f prime of 2. So we need to find f prime of 2. F prime of 2. So we start with f of x, that's x squared plus 1. We find f prime of x, that's 2x. We find f prime of 2, that's 2 times 2. F prime of 2 equals 4. So g prime of 4 is 1 over f prime of 2. Right like that. Let's do one check for understanding problem, and then we'll be all done with these notes. If f of x equals 1/4 x squared, and g of x is the inverse of f of x, and g of 1 equals 2, what is the value of g prime of 1? Go ahead, pause the video, try that on your own, restart the video when you're ready. Here's what I got. Because g and f are inverses, and 1, 2 is a point on g, that means 2, 1 is a point on f. So g prime of 1 is going to equal 1 over f prime of 2. We're going to find f prime of 2. So we start with this, and then we take the derivative, so that's 2/4 or 1/2 x. When we plug 2 in for x, we get 1. G prime of 1 is going to be 1 divided by that number, so 1 divided by 1. G prime of 1 equals 1.